8.5, modelling with vectors, the last part of the AS vectors notes. We have come across most of this in mechanics, and we can do modelling with vectors in other ways, but this is the main place where we would use it. So we've talked about vectors having both magnitude and direction, so an example of that will be velocity and displacement. Their corresponding scalar quantities are speed and distance. So if you are asked about the distance from A to B, it is the magnitude of the vector A to B, of the displacement A to B, and the same with velocity and speed. So we're finding magnitudes, and you should have seen that when we've been working with it in mechanics. For an object moving with constant velocity, that is important that I'm focusing on constant velocity here. We have this formula: velocity is equal to displacement over time. In mechanics, you can see all of this with the Suvat equations. So we can use the Suvat equations in vector form, and that shouldn't be an issue. But because we've got constant velocity, we've got A is equal to 0, which has reduced the formula down to this one here. So having a look at example 8.5.1. So an object initially at 12I plus 27j meters, so that's its initial position vector. So remember, when we're using the ij notation, we are going relative to an origin, so relative to that point there. So this is the vector here. We've got 1227. This diagram hasn't been drawn to scale at all. And then we have another position vector. So we're moving with constant velocity. 10 seconds later, we have position vector 15I plus 11j. So that's what our diagram looks like. And in terms of our motion, we started here. So that was at t is equal to 0. And then we travelled in that direction to finish here at t is equal to 10 seconds. So, and then that's our positions relative to the origin. When we are modelling, it is up to us where we put the origin. So we talk about the origin as being the coordinate 0, 0, but technically I could place the coordinate axes anywhere that I want to, and therefore that's how we come up with these position vectors. So we are asked to find its velocity. So in order to do that, I want to use the formula at the top of the screen. So I want to use displacement over time. I need to work out what my displacement is, and using the methods that we've already seen, if I am starting here at point A and I'm finishing at point B, my displacement is the vector A to B. So to calculate A to B, I am going to go back along this line here. So going backwards, I've put the minus sign, and then I am going forwards from O to B, so that gives me 15, 11, and that is going to give me my displacement. So minus 12 plus 15 is 3, and minus 27 plus 11 is minus 16. So that is our displacement for the question. So then, in order to find the velocity, we're doing it as a vector, so I'm just going to underline it. We are using displacement over time. So the time is 10, so 1 over 10 times the displacement, which gives me the velocity vector of 0.3i minus 1.6j. Remember, when you are in a modelling question, you must put your units on there. Okay, so we've got the velocity of that. The speed then is the magnitude of this vector. So to work out the speed, we're just doing 0.3 squared plus 1.6 squared. Remember, we said we don't need to worry about that minus sign, because we know when we square minus 1.6, all squared would become positive. And then I'm going to give my answer to 3 significant figures. So that's 1.63 meters per second to the minus 1 into 3 sig figs. So that's just applying it to a mechanics question. Moving on to the next question. So we've got example 8.5.2. Again, diagram drawn. A lot of exam questions, you do get a little bit of a diagram to help you out. So a girl walks 2 kilometers due east from a fixed point. So this is a starting point. Again, we're calling it O, and she's walking to point A. I have defined north to just be straight up the page. Obviously, you can put north wherever you wanted it to be, and east would just be at 90 degrees to it. So that is up to you how you do that. But generally, we run north along the y-axis, just because it seems to make logical sense. We're going from the origin to A, that's 2 kilometres away. And then from there, she's going due south, and she's going 3 kilometres. Again, not drawn to scale. To get from A to B. So we want to find the total distance travelled. So first of all, the total distance travelled. Distance is just how far we've gone, started there, 2 there, 3 there, 5 kilometres. The position vector. So the position vector of B relative to that starting point. So that's O to B is what we are looking for. So this vector here, O to B, going in that direction, we're going 2 across, so 2i, and then we've got 3 down, so the position vector would be 2i plus 3j. C, find the magnitude of O to B, so that would be the length of that line there, which you can do in vectors. You can just see that from having the right angle triangle, and really that's all vectors are. It's just things like east and south, and considering it in those 2 perpendicular directions. So we are just doing the square root of 4 plus 9, so the answer is root 13. And then to finish off, the bearing of B from the origin. So the bearing of B, so remember when you do bearings you need to put your north line in. So of B from the origin, so I'm looking for that angle there, which I'm going to call theta. In order to do it, I'm going to find this angle here. So we're just using tan alpha, which is equal to 2 over 3. So I get alpha is equal to 33.7 to 3 significant figures. To find theta, then we would just need to do 360 take that. So again, a lot of that should be things that you've seen before, but it's just putting it into the context of vectors. Using vectors, we can do quite a lot of different topics. So you might see something like this. A more complicated version of this would involve using the cosine rule and the sine rule. Ultimately, if you have a triangle and you know its position vector of the position vector of the vertices, then you are able to find the length of that vector. So here it was quite straightforward because we knew the length of that line there was 2 and the length of that line there is 3, which made it a lot easier. But if it was so that she was travelling at an angle, so she was working on a bearing, then we would be able to use trigonometry, sine and cosine rule. So we will have a look at some questions like that as well, just to tie it into this topic and to finish it off. Okay, but just remember, ultimately, magnitude gives you the length, and then direction gives you the angle. If you get those 2 points, you should be able to apply it to all the different vectors questions that you come across.